So, hello everyone. Thanks for tuning in. I'm Yavuz Oz, and I will be presenting an overview of my PhD work. My focus has been the nature of the transport current path in state-of-the-art 2212 round wires and characterization of hysteretic losses. Okay, so here's a brief outline of my talk. I'll start with my motivation, and then I'll detail my study of oxygen doping and connectivity in 2212 round wires. You can actually find a preprint of our paper on archive. And then I'll move on to the characterization of, oh, that's not supposed to happen. I'll move on to the characterization of hysteretic losses. So let's start with why 2212 matters. Bismuth 2212 is the only high field, high JE, isotropic, round wire, high temperature superconductor. And as such, it's a very promising candidate for magnet applications above 25 Tesla, which is the LTS limit. So here in this plot, you can see how Bismuth 2212 has very favorable whole wire critical current density characteristics at high fields. And the round wire form is really important because it's ideal for magnet applications because it allows multifilamentary architectures. It allows the conductor to be produced in multiple multifilamentary architectures, which makes them robust to local defects, unlike REPCO, where effectively there's a single filament. And these round wires can be twisted to lower hysteretic losses. And as I'll show later, with 2212, you can achieve LTS level hysteretic losses, unlike REPCO or Bismuth 2223. I'm not sure why, I'm sorry, for some reason, the animations seem to be auto-advancing. Okay. Right, so round wire 2212 can be flexibly cabled like LTS using mature LTS manufacturing techniques, which is a huge plus. And despite Bismuth 2212's intrinsic electromagnetic anisotropy, very high anisotropy, in round wire form, it's actually macroscopically isotropic, much like LTS. Partly that's due in part to the slow rotation of the c-axis of 2212 grains along the wire axis. So it's 2212 is the high field LTS at low temperatures. Okay, so we're getting very high JC values with 2212, but how close is 2212's JC to the theoretical maximum, which is the depairing current density? And when we calculate that, we see that JC is less than 1% of the theoretical maximum with 2212, and compared to NIPTI or REPCO, which is at 20 to 30%, that's really low. So we conclude that the effective cross-section of the current path is strongly reduced, and there's a lot of room for improvement. And there's various factors that can limit JC, the chief of which can be grain boundaries. And I'll detail those later. So the aim of my PhD work has been to understand the supercurrent path in state-of-the-art high JC 2212 round wires and characterize hysteretic losses. As I mentioned, there are multiple factors that can limit JC in multifilamentary 2212 wires. There's physical factors like secondary phases, cracks, voids, filament cross-section variations, and then there's electromagnetic factors, there's low angle, low JC grain boundaries. So I've studied using macroscopic measurements how grain boundaries act when deoxygenated how filament-to-filament superconducting connections affect hysteretic losses, and how these factors limiting JC affect the distribution of JC in 2212 round wires. And now this work is being led by fellow graduate student Shyam Barua, who's recently published a paper on it at ASC 2020. Okay, so I'll move on to further experiment on oxygen doping and connectivity in 2212 round wires. So a short background on the grain boundary problem with HTS. Very early on with YBCO, an exponential decrease in grain boundary JC was demonstrated with increasing grain boundary angles past a very low critical angle of 2 to 3 degrees. And later on with 001 tilt grain boundaries in 2212, the same was demonstrated, and also I believe with 2223. So the high angle grain boundary problem has been a major impediment to progress with HTS, and it's exactly why REPCO and bismuth 2223 have to be made in tape form to texture so that high angle grain boundaries can be minimized. So here you see an illustration of a sketch of what biaxial or uniaxial textures look like in YBCO and 2223. The interesting thing is that 2212 round wires can be made like LTS wires without extra steps to achieve texture, and achieves very high JCs at high fields. But interestingly enough, bismuth 2223 can only achieve about 1/6 of the JC of 2212, and it undergoes complex, time-consuming, expensive process to texture the tape. But 2212 and 2223 are very similar at an atomic level. So how is it that 2212 can perform this well, especially in round wire form, whereas 2223 can't? So this paradox prompted the investigation of growth textures of 2212 and 2223 by Dr. Fumitake Kametani at ASC. So here I'll present an overview of his work. So here you can see grain orientation maps of longitudinal cross sections of 2212 and 2223 wires generated using electron backscatter diffraction imagery. And you'll notice immediately that bismuth 2212, the image for 2212 is dominated by a green color, which indicates that there's a strong A-axis texture, meaning that the A-axis of the grains are aligned with the filament axis. And then with 2223, you can notice that there's an abundance of blue color, which means that there's a high in-plane misorientation. Okay, so an orientation map of 2212 and 2223 reveal that in-plane rotations, which are along about a fixed c-axis, and out-of-plane misorientations in 2212 are mostly constrained to 15 degrees, whereas when we compare that to 2223, the out-of-plane rotation distribution is somewhat similar, but there's basically no in-plane alignment in 2223. It's random. So here's a rough, crude sketch of what grains might look like if we had viewed them from the top. The 2212 grains are much better aligned in plane, but 2223, as you can see, is basically randomly stacked. and 2212 grains are much longer. I think I forgot to mention that in the earlier slide. 2212 grains are much longer than 2223 grains. So it's not just that 2212 has much greater JC than 2223, but it was also measured that 2223 has significant JC H hysteresis, field increasing, field decreasing JC hysteresis, which is an indication of weak links in the supercurrent path, in the transport path. But 2212 does not seem to exhibit such a feature. So we conclude that there's a strongly coupled current path in bismuth 2212 round wires as opposed to bismuth 2223 tapes, where there's weakly coupled grain boundaries in the current path. So how is it that 2212's current path is strongly coupled despite the distribution of misorientations which exceed the very low critical angle? So to be able to answer that, we need to go back to early models for current flow in bismuth 2223 tapes. So the first model that emerged was the so-called brick wall model, where current is postulated to weave around AB plane obstacles, and polycrystalline JC can be high enough if the aspect ratio of the grains confer a large grain boundary, basal plane face grain boundary area that makes up for the weak coupling of the C-axis planes. And a later model emerged, which is called the railway switch model, which favors a network of strongly coupled small angle C-axis tilt grain boundaries. It's important to note that both models predict the active cross-section to be small and C-axis transport JC to be an important factor limiting the JC of the conductor. So the hypothesis that was put forth was that the better alignment and the large grain boundary area in 2212 enables strongly coupled brick wall type current flow. So there's past evidence for C-axis transport signature in 2223 tapes. The better in-plane alignment of 2212 likely increases the C-axis twist JC, and the large areas available for C-axis transport makes up for the, as I mentioned, the weak coupling of in the C-axis direction. So this grain boundaries, C-axis tilt grain boundaries might have lower JC, but the area might make up and have enough IC. Furthermore, there have been bicrystal studies on artificially grown 2212 bicrystals with a 001 C-axis twist grain boundary setup that have been shown to be strongly coupled. So one such plot shows a grain boundary to grain boundary IC to grain single crystal IC ratio that is independent of the misorientation angle with 2212. Now, an alternate hypothesis was that strong oxygen overdoping increases grain boundary transparency in bismuth 2212. And that's the hypothesis that I set out to explore. So high temperature superconductors have higher JC when strongly overdoped. And bismuth 2212 is the only cuprate that can be strongly overdoped as opposed to 2223 or YIPCO. And overdoping with oxygen can improve JC by transforming weakly linked grain boundaries that are thought to be oxygen deficient with respect to grains. It can reduce it does reduce the anisotropy of bismuth 2212, and it improves vortex spinning strength. So I underdoped, transport JC optimized, and fully oxygenated, meaning strongly overdoped 2212 round wires using secondary heat treatments to remove oxygen and see how they would behave. So we progressively underdoped samples using a quench furnace. We took JC optimized samples, originally heat treated at high pressure and 1 bar oxygen partial pressure. So here's the heat treatment. And then we subjected them to secondary heat treatments at 100th the original oxygen partial pressure to extract oxygen following this kind of regimen, and then quenching the sample at the end to lock in the doping state. And the samples I used were OSD manufactured wires using previous generation Nexans granulate. They were 37 by 18 wires. I should note that newer wires produced with the state-of-the-art NGMAT powder actually achieve, I think, more than twice the JC. So what happened was, when you look at the TC plot, it changed parabolically, which means that we succeeded in underdoping the samples. And then if you look at the irreversibility field, which is a measure of the vortex spinning strength, and transport JC, they were both severely suppressed as we underdoped the wires, which was expected behavior. What was not expected was that we did not see any weak link signature at any doping level, meaning JCB hysteresis, as I mentioned in the earlier slides. So if you compare these results with the earlier plot that I showed for bismuth 2223, it's very obvious that there's no JCH hysteresis, or no appreciable JCH hysteresis in even the most underdoped 2212 wire that had the lowest JC. And again, we see an electron backscatter diffraction grain orientation map, and there's a very strong A-axis texture, and grains can plastically bend to accommodate each other and form larger area C-axis twist grain boundaries. Okay, so quick summary. Presently optimized quasi-biaxial texture of 2212 round wires intrinsically constitutes a strongly coupled current path, regardless of the oxygen doping state. So the oxygen doping does not seem to affect the transparency of grain boundaries appreciably to turn them into weak links. Most grain-to-grain contacts occur by basal plane phase grain boundaries, so C-axis twist grain boundaries, enabling brick wall type supercurrent transport. And as I mentioned, 2212 round wires defy earlier assumptions that high angle grain boundaries have to be eliminated and the conductor has to be textured to be useful. And as such, it's very interesting, and it merits more detailed investigation. So to that end, I will not go into detail, but I am actually trying to extract single grain boundaries or colony boundaries from 2212 round wires using a focused ion beam setup with fellow PhD student Aviola Olaya. And we plan on conducting transport and resistivity measurements to probe the nature of 2212 grain boundaries directly. Okay, so next I'll talk about hysteretic losses in 2212 round wires. Okay, so on the left we can see an unreacted cross-section of a 2212 wire. The filaments are mostly discrete, and ideally magnetization would arise only due to shielding currents confined to individual filaments. Sorry. But what happens is that charging a magnet made of multifilamentary wires drives eddy currents across the silver, the normal matrix, coupling the whole conductor and greatly enhancing the hysteretic loss above that due to the magnetization of the individual filaments. But luckily, twisting, I'm really sorry, I don't know why this is happening. Twisting the wire can reduce losses toward the intrafilament baseline at short enough twist pitches, and effectively decouple the conductor. So in 2212 round wires, there's an additional and significant loss component. 2212 is multifilamentary when delivered to the user, but it's not yet superconducting. Again, in the unreacted state, the filaments are discrete. And they're confined to their cavities. But after the heat treatment, filaments can touch or merge together, as you can see in the SEM image on the right. This is an unfortunate side effect of the high pressure 50 bar heat treatment that we have optimized for the highest JC, and it causes filaments to merge as we wait in the melt state. Okay, so there are two types of bridging connections. Type A bridges are 3 to 5 micron thick grains that span the width of 2 or more filaments, and they're assumed to be high JC interfilamentary current paths. They can greatly enhance hysteretic losses. Then there's type B bridges. They are thin outgrowths that can touch each other. And unfortunately, 2212 wires with densely packed filaments suffer from heavy bridging produced during the partial melt heat treatment that generates high JC, as I mentioned. And I should also say that we do not believe type B bridges significantly enhance losses. So what I've done is I took, I'm really sorry, I took state-of-the-art 2212 round wires made with NGMAT powder and compared them to previous generation state-of-the-art round wires made with Nexans powder. And I also compared partially bridged wires to wires with discrete filaments to compare bridging induced losses to basically eddy current losses. So here's a brief overview of the samples. The first one is a densely packed 55 by 18 wire with NGMAT powder. It has the highest JC. The filament diameter is approximately 12 microns, so very fine. And the bundle diameter is approximately 130 microns. Note that the diameter values are measured using unreacted wires. So the diameters do change after the reaction. And then we also had 3 sample sets with previous generation lower JC Nexans wire with a 37 by 18 distribution configuration. And as you can see, there's a lot of type A bridging in these wires. Then I compared the results for these wires with a 27x7 wire made with Nexans powder, and you can see that the filaments are discrete with some type B connections, but we believe these wires to be effectively decoupled, but our results will speak for themselves. Okay, so so to measure losses, we use the standard ITER procedure. Samples were wound and reacted on an Inconel 600 screw with a 5mm diameter. And straight sections were used for IC measurements at 4.2 Kelvin and a 5 Tesla field applied perpendicular to the wire axis. And then we calculated JC by dividing IC by the optically measured 2212 cross section. And just to remind again, the area of 2212 was measured optically before the heat treatment. And then magnetization loops of approximately 94mm coils were measured in the VSM. And then I integrated these to calculate losses for a 3 Tesla maximum field. And the magnetization at 5 Tesla was used to calculate the effective filament diameter using the critical state model formula for a cylindrical superconductor in a transverse field. So here are the results. First, transport JC. The mean JC for state-of-the-art wires with NGMAT powder is roughly 5,300 amps per millimeter squared. Despite some fluctuation around this mean, JC seems to be independent of the twist pitch. And then the previous generation partially bridged Nexans wires also seem to have JC independent of the twist pitch, despite some fluctuations. And the mean JC is about 70% lower than that of state-of-the-art wires with NGMAT powder. And then we have the transport JC for the non-bridged Nexans samples. They had about 18% lower average JC compared to partially bridged Nexans samples. So they had the lowest JC. So we can see the hysteretic losses normalized to wire volume. They monotonically decreased with increased twisting. So the minimum for NGMAT wires was only slightly higher than the ITER hysteretic loss maximum specified for reference niobium tint strands. Unsurprisingly, the lack of bridging in 27x7 wires enabled very low losses, and the dominant coupling mechanism, like we believed, is eddy current coupling, which twisting reduces very effectively. Okay, so hysteretic loss per superconducting volume offers a better comparison, as the JC increase going from Nexans to NGMAT powder is twice as much the increase as the hysteretic loss per 2212 volume. And of course, losses were even lower with the non-bridged wires, and you can see that twisting was twice as effective at reducing losses in the non-bridged 27x7 wires. The effective filament diameter of the non-bridged 27x7 wires reduced significantly down to a value 3 times the filament diameter. Though this implies that there's still some coupling present, we indeed know from ramp rate measurements that the filaments are completely uncoupled, as they displayed logarithmic behavior or logarithmic dependence on the ramp rate. So one factor that might be playing a part in this discrepancy is the non-cylindrical shape of the filaments as opposed to the cylindrical geometry assumed by the critical state model. The other reason is that although the transport IC is limited by the weakest links in the 10 millimeter long cross-section, regions of varying JC that make up the entire cross-section contribute to magnetization, and they amplify the effective. And magnetization current loops of different JCs and unknown length scales contribute to magnetization. So here you can see the distribution of JC in our 2212 wires and an equivalent NGMAT wire, and you can see that the 1 microvolt per centimeter criterion roughly represents the mean IC. For details, we see Shaun Barrios' manuscript. So these factors produce anomalously large the effective values. So at least in the context of this study, the effective should be thought of as a measure of magnetization normalized to transport JC. Okay, so next, you see that although the untwisted NGMAT wire and the untwisted or non-twisted non-bridged Nexans wire had similar the effective values, twisting reduced the effective only marginally in the partially bridged 55 by 18 wires because of substantial interfilament coupling that generates supercurrent loops on scales smaller than the twist pitch. Excuse me. And for all other twist pitches, the effective for the 55 by 18 wire that's partially bridged is larger than the bundle diameter, and this would normally imply an intra or even inter-bundle bridging, but we have not observed inter-bundle connections in our 37 by 18 wires, nor in our 55 by 18 wires. Like in the non-bridged wires, the effective filament diameter values are anomalously high, likely due to the distribution of JC and the non-cylindrical shape of filaments. Okay. When we compare the highest JC NGMAT samples with the previous generation partially bridged Nexans powder samples, all twisted and untwisted NGMAT samples had lowered the effective, which is good news because normally losses scale with transport JC. We believe there's two effects that enable a reduced the effective. One is that we've noticed reduced bridging in the 55 by 18 wires with the NGMAT powder. And we think this is due to the reduction, due to the re-optimization of the heat treatment to the new powder that reduced the amount of bridging. And as I mentioned, connectivity improved in NGMAT wires. So the measured transport current measured using the criterion is more representative of the JC of the entire conductor. Okay, so to conclude, the switch to state-of-the-art NGMAT powder reduced transport JC normalized losses in 2212 round wires, which is again good news because normally losses scale with transport JC. Again, we believe that two positive effects are responsible for this. Reduced bridging brought on by re-optimization of the heat treatment. And improved connectivity in the state-of-the-art NGMAT wires. And it's also important that these state-of-the-art wires achieve the minimum wire volume normalized losses of about 590 kilojoules per meters cubed, which is only slightly higher than the ITER maximum. So this is very impressive because the JE at the same 12 Tesla field of our samples is 50% higher than that of the niobium tin ITER reference strands that I compared them to, measured circa 2016. So our results show that by mitigating filament bridging, it's possible to maintain hysteretic losses in state-of-the-art 2212 wires at acceptable levels while still significantly improving JC. And these results highlight 2212's utility for ultra-high field, low hysteretic loss, high field quality magnet applications. Thank you. Questions?